Hello and welcome to EP2P04. This is going to be topic number 3, moments and 3D static equilibrium. Before we get into that, we're going to talk about how torque about a point works, and even before we get into that, we're going to review some more information about vectors. This is going to be a very vectory week, starting off with position vectors. Rather than specifying a point by giving 3 coordinates in round brackets, we can specify it by a position vector, which gives 3 displacements in square brackets. So these 3 displacements, displacement in x, y, and z in a Cartesian coordinate system, that's where the x, y, and z axes are perpendicular and just indicate the distance away in that perpendicular direction from some origin point. The position vector tells you what the displacement you would have to take would be, what the displacement from the origin that you would take to get to this point. So you can say the point is located at these coordinates, or you can say, with a position vector, here's what displacement you need from the origin to get to that point. Kind of a very subtle distinction there, but it's important because now we can deal with position vectors in order to specify locations. All right, so let's convert a vector to a point. What point corresponds to this position vector? 1, 2, 3 in the triangle brackets. Remember, that's another way to represent a vector, not just this square kind of column notation, but this one is also a way to specify vector. And the answer is just the same things, but in round brackets to specify a point. What is the difference between the position vector and the point? The point is the location, whereas the position vector has a magnitude and direction like any vector, and is the way to locate the point, is a way to get to the point by starting at the origin. It tells you the displacement you would take to get to that point. Okay, let's find the vector between 2 points. So once we've got 2 position vectors, R1 and R2, how do we find the displacement vector between them? Well, we subtract them. So the displacement from point 1 to point 2, from R1 to R2, is R12. So you'd read this as the displacement from 1 to 2, or R12, which is R2 minus R1. So the final point minus the initial point will give you the displacement between them. Let's also think about this graphically. If we've got 1 point there, R1, let's imagine that we have an origin. I guess we can draw that in. So I'm going to hold Shift and make things that are perpendicular, and then press T to get like X and Y. We'll show this in 2D, but it could be in 3D as well. Okay, so now that's our position vector R1. There's a lot of turning bold on and off to get this to work properly. Maybe get the 1 lined up really nice there. And maybe make it a smaller thing for, okay, so there we go, R1. And what if we've got R2 over there, which would be, back to 16, R, and back to 12, 2. Okay, so there's R1, there's R2. These are the vectors. These specify the points, this point there, and this point there. Point represented by R1, point represented by R2. The displacement from 1 to 2 should be this vector, right? We start here, and we go down to that point. This vector is the R12 that we're looking for. So turn off the bold there. There. So this is what we're going for there. Now let's check. We said that we should be able to get R12 if we take R2 and subtract R1. How can we do that graphically? Well, we can start with R1 here and get a negative version of it by starting at the end and like drawing it like that, and then just displacing it around there, right? So if we wanted to take R1 and subtract R2, if you think about this vector addition where you just put them tail to tail and then look at the this is one way to look at it. Even you don't even have to do this other construction here. You could think of this as being, all right, we got R2, and if we want to get R12, we just put them tail to tail and then go this one to that one. That should be R12. But another way to think about it is to say, well, I always like to add things that are kind of tip to tail, right? So take negative R1, like we've got here, negative, let's make this a little bit bigger, negative R1, yeah. So then R2 minus R1 should be this vector, right? So let's check. This vector from there to there, that looks a lot like our R12. Let's see how we did. Yeah, pretty good. So this seems like we get the same vector that way. You can see that by subtracting R2, taking R2 and subtracting R1, we get the same thing as if we were to go from the point represented by R1 to the point represented by R2. So that indeed is the displacement between vector R1 and R2. So that's the graphical implementation. We could also do an algebraic implementation by just subtracting their components. So R2 has an x component of 3, R1 has an x component of 1, so we'll take 3 minus 1 to get 2, 7 minus 2 to get 5, and negative 2 minus 4 to get negative 6. All right, we also can calculate the length of this vector by taking the magnitude of it, which is the distance from point 1 to 2, which would be R1, 2 with these double bars around it. By the way, these things that I drew are in 2 dimensions. They're not these vectors. This is just like an example of how you would find the displacement between any 2 arbitrary vectors. Yeah, maybe we should write something about this. This is not exactly the R1 and R2 shown. You know what? Maybe let's kind of modify this. Let's say, let's figure out what these are, right? So if this is X and this is Y, then R1 looks like it's about maybe 2 in the X and 1, 2, 3 in the Y. So another example, R1 equals, let's do 2 dimensions, 2, 3, and R2 is equal to maybe like 2 and just a 1, right? This is pretty rough. So actually this goes slightly more to the right than that, so maybe we'll make it like a 2.1. Okay, so then R12 should be equal to R2 minus R1, which is this component minus this component, and that'll be negative 0.1 and negative 2. And that seems about right for what we got there. So the graphical is lining up with what we have algebraically. If we wanted to know the magnitude of this, we could, yeah, that's the symbol for that. There isn't actually a hotkey for this one in math type by default, so you have to assign it. In case anybody's using math type and cares about that, you can go, the way that I do this is you hit F5 to bring up this menu, find the symbol that you want, like, I don't know, Dell symbol or something, and then go into Preferences, Customize Keyboard. Oh, wait, that's not it. Preferences. Wasn't it that? Yeah, there we go. I must have hit the wrong thing. Customize Keyboard, and then Recently Used Symbols and Templates. Way easier to find it there. And then you find the thing that you just used, Partial Derivative, which I've got assigned to Control KD. I think I might have assigned that. I'm not sure if it actually is that by default. Anyway, enter the new shortcut key that you want, and then you get the some easy to use hotkey for yourself. Anyway, this R12, this norm of this vector, would be the root of the sum of the squares of its components, which would be root of 4.01. And that's going to be basically still 2. All right, so that's kind of like one way to do it, but that's a bit of a distraction from what we were doing here. What we'd also like to do is find out how to do this with Maple. Yeah, so this is like maybe a check. We'll leave this down at the bottom here. How do you do this with maple. How do we do this addition here? Well, there's a couple of different things that we're going to need. We are going to need to know how to define vectors. And you do this just with triangle brackets, right? So 1, 2, 4, and 3, 7, negative 2. R1 is 1, 2, 4. R2 is 3, 7, negative 2. When you're doing this, try and probably a good way to learn it is to check out the commands, try them out, and then see if you can use them without looking at them and change them around, see how it works. Okay, so what we can do is just subtract these to find the distance between them, and then we could take the norm by using the root of their dot product. This is the dot product operator for vectors there. Yeah. So we can actually check that maybe for this one instead. Let's go with R1 is 2.1 and 3. R2 is 2 and 1. And yeah, let's subtract them. R12 is R2 minus R1. Did we do it correctly? Yeah, negative 0.1 and negative 2. You can see because we had a decimal, it turned maple into floating point math there, and now we've got, by taking 2.1 minus 2, according to the computer, is just slightly less than negative 0.1. Interesting. So there's some round off error for you. Okay, let's check the magnitude of this. Dist12 should equal the root of R12 dotted with itself. And yeah, almost 2, just slightly more than it. What else could we do? We could include some of these packages. The linear algebra package is the one we're going to use most of the time. Although it's less convenient for this one norm function to find the magnitude of a vector, it is convenient for a lot of other things like cross product and all that. So with linear algebra, then we'll take dist12 check is equal to norm of R12 2. We've got to give it the 2 norm. So 2 norm means you take the root of the sum of the squares of the components, as opposed to just taking the 1 norm. Let's see how that works. That is the absolute value of each of the components then added together and not rooted afterwards. So this is not the one we want most of the time. It's important in linear algebra. There's all kinds of different classes of norms that you could use, and what we are interested in for distance is the 2 norm. If this is too much, you could always just use this root of the dot product trick instead. Okay, so a point force F applied at a point RA to an object creates a torque about point RO of tau, the vector, is equal to the displacement from RA to RO, this thing's called the moment arm, crossed with the force F. So this RA minus RO is the vector from RO where you're finding the torque to the point RA where the force is applied, and again is called the moment arm. Okay, let's have a look here. I've got this 3D thing in Paint 3D that I've sketched up here to show this. This is for the force F1. Let's imagine point A down here is the origin. So we've got RA specifying the position where force 1 is applied on this object. And then we've got RO, which is the location of where we're going to find the torque. You can usually choose to find the torque about whatever point you like when you're solving the problems later, but now let's just talk about what that means. So once you've got a point, you're going to find the torque that this produces about. What you do is you need the moment arm, which is this ROA here, the vector from point O to point A, which, like before, is final minus initial. So this vector, ROA, crossed with F1, will be the torque that F1 creates about the point ROA. You see, you don't need the point that you're finding the torque about to even be on the object. You can conceptually calculate the torque that this creates about that, whether it's on the object or not. So by the properties of the cross product, the torque vector is going to have a magnitude equal to the magnitude of this thing times the magnitude of this force, the moment arm times the force, times the sine of the angle between them. If we look at the vector here, The angle looks like it's about 120 degrees, a little bit more than 90 degrees. So the sine of that is going to be still pretty large. For the direction, it's going to be perpendicular to both of them. Cross product of this vector with this vector will always be perpendicular to both of the vectors that we started with. Now, what the right-hand rule does is just decide which of the two possible perpendicular vectors it could be. So you can see if we make the plane that has both of these in it, kind of like that, we could get one that either goes that way, over to the right here, or that way. And the right-hand rule just helps you decide between those. So if you take this vector, cross this one, fingers along that, and then curl in this direction, your thumb will point out of the page. So it's this one that goes to the left, right? Yeah, I think that makes sense. Okay, so this is a little bit tricky to do in Paint 3D. I'm gonna try it out. Bear with me here. If I'm rotating around and moving this thing, that looks okay. How's that for this one? Ooh, not quite perpendicular. Let's try there. So it seems perpendicular to the blue one now, and still perpendicular to the force vector. That looks pretty close. Okay, so the combination of ROA and F1, when you find the torque that F1 produces about this point, it'll be a vector that comes out of the page like that. The magnitude is maybe not right, depending on what the units of distance are. So we don't have the same scale for force and distance on this graph. So the magnitude is not necessarily off. We could just be scaling the force differently than we're scaling distance. I mean, this might be kilonewtons or newtons or something, and then maybe this is centimeters. So as long as the line length is consistent within a given unit, so if F1 is about the same length as F2, it means it has to be about the same size, then we're in pretty good shape. The torque doesn't have to be the same. It's in different units, so the length of this doesn't tell you too much if you know the length of these other ones necessarily. You can change the color, by the way, in Paint 3D to something different up there. I don't know, maybe like a purple one, and then put in a label like this, which we could say T1, and then change this to the symbol font. Ah, there we go. Great. And even make it bold in this. That's kind of cool. So there's our torque produced by the cross product of those two vectors. What this means is that about this point, this force has a tendency to cause rotations in the direction that's out of the page. And using the right-hand rule again, that means counterclockwise. So this force tends to rotate things counterclockwise about that point. You can sort of visualize this too. This would be pulling things around that way, yeah? The torque that it creates depends on the point you're finding the torque about. Let's look at some points here. So we talked about moment arm. This is the distance, this displacement vector from where you're finding the torque to where the force is applied is called the moment arm. Cross that with the force to get the torque the force produces about that point you're finding the torque. Point force means a force applied entirely at one point. That's what we are drawing when we draw these forces. We say it's just applied right there, point force right there, point force right there. Really, there's no such thing as this. The force is actually going to be distributed. So over some small area, at least, there's some contact point. If you were to zoom in, you'd see it's not really a point, right? I mean, this is just kind of showing the arrow thing here, but it still gets, I think it gets the concept across, which is that the force is really going to be distributed over some area of surface at least, or maybe for something like gravity, distributed over some area of some region, some volume within the object. If the force is equal to 0, it's going to produce no torque, because then this cross product would be 0 because one of the vectors has no length. If, similarly, the moment arm is parallel to the force, it produces no torque. What does that mean? That is if this moment arm is parallel to this. So imagine we're finding it not about this point, but we want to find the torque that it produces about, let's say, this point. Now this has a moment arm that would then be parallel with that force. So the cross product would involve taking the sine of 0 degrees, and sine of 0 is 0. With no angle between the two vectors, then you get a cross product of 0. Oh, yeah, one other thing. With this cross product thing, sometimes people get confused on what the angle is between the two vectors in this. So, like, do we use this angle, or do you have to kind of continue this and then use this angle here, the smaller angle, like the angle of the difference between them? Really, that's the one we mean when we say the angle between them. But you can also use this one, since that's just off by 180 degrees. And from trig, we know that sine of pi minus theta is sine of pi cos theta minus cos pi sine theta, right? Using the sine sum angle formula and the parity for sine of theta. And sine of pi is 0. And cos of pi is -1. So therefore, sine of pi minus theta is also sine of theta. And that means if you wanted the sine of this angle, it's the same as the sine of this angle, because this angle is pi, which is 180 degrees, minus this one, right? So this is pi minus theta, this is theta, and we just showed that the sine of those two things is the same. So that means it doesn't matter which one you use. In cross product, you can call this thing the angle between them, or you can call that thing the angle between the vectors, and you're going to have the same result. All right, we'll come back to point 5 in a minute, but first let's get an example here. A 2-meter cube, meaning that it's a cube that has a side length of 2 meters, so 2 meters by 2 meters by 2 meters, is entirely in the first octant, the part where the x, y, and z are 0. You might have heard quadrant talked about in like the XY plane. Quadrants are the ways to break it up into like positive x, positive y, then negative x, positive y, negative x, negative y, and then positive x, negative y. I think I said that right. So that's the quadrants that you could divide up the XY plane into. Well, in the XYZ space, it's octants, because instead of those 4, for each of them there's positive and negative z, so you have 8 different parts. All right, the first octant is where they're all positive. I'm not sure how you number the rest of the octants, but I'm sure there's some method that that mathematicians like. Anyway, so one corner at the origin, so this means the cube is entirely in the first octant, one corner at the origin, so the other corner is at 222, right? First, what are the coordinates of all the cube's corners? So those would be just the parts at 0, 0, 0, then 0, 0, 2, 0, 2, 0, 0, 2, 2. It's kind of like counting in binary, except using 2 for the yes instead of, or true instead of 1. Right, so here's the coordinates of all the corners. Next, suppose we've got this force, 2, 4, 5, applied at the farthest corner from the origin, which would be 2, 2, 2. Find the net torque that this force makes about the origin and about the corner at 2, 0, 0. All right. For this, we're going to need cross product. So how do we calculate a cross product? I guess first let's just talk this through kind of analytically. So to find the torque that this makes about the origin, we would say, maybe we'll use this symbol, torque about the origin is equal to the RA minus R of the origin crossed with the force F1. Actually, maybe since this is force 1, we'll use like a 1A or something to say where force 1 is applied. Okay, so this would be the torque that it creates about the origin. Let's work it out. So R1A is its location, 2, 2, 2, and we're going to subtract off the origin, which is the 0 vector in position vector, so 0, 0, 0, and then cross that with F1, which is 2, 4, 5. The units are going to be the same. These are all in meters, and these are all in newtons, so we can just take this out at the start and not have to rewrite it for every single term there. All right. So the concept of how we got this is the location where the force is applied minus where we're finding the torque is the moment arm, and we're going to cross that with F1, which is the force vector. Okay, so here's how you do this algebraically. We will have, continuing the line from the last one, so we'll just put an equals there, 2, 2, 2, crossed with 2, 4, 5 in Newton meters. And to get a cross product, I like to use the determinant method, where we've got the unit vectors I, j, and k along the top, and then put the first vector you're crossing as the second row, and the second vector you're crossing as the third row here. Yeah, Newton meters. Okay, so now think about what you would get for the, to figure out what you would get for I in this thing. It's this times the determinant of what's left over here. Or if you like the kind of 3 by 3 determinant trick, you can go this times this times this minus this times, go through the wall, this times this. Ends up being the same as the determinant of this little 2 by 2 there. Either way, you get 2 times 5 minus 2 times 4. And for j, 2 times 2 minus 2 times 5. For the wall trick, the middle one is a lot easier. You go this times this times this minus this times this times this. For determinants, you need to remember that it's negative determinant, the determinant of what you get when you cross out the first row and second column. So I'm pretty sure that thing is called, that determinant is called the 1-2 cofactor, I think. Okay, so we've got this times, so that determinant, but then multiplied by a -1 because this is in position 1, 2, and -1 to the power of 1 plus 2 is still negative. So that's some linear algebra reminder there. All right, next, k will be 2 times 4 minus 2 times 2. So that's this times this minus this times this. We're in a spot where we have a positive 1 in the grid again for this cofactor expansion. So yeah, next we can work this out. What do we have here? 10 minus 8, and then we've got 4 minus 10, and then we've got 8 minus 4. So we should get 2, -6, 4. Let's check if that works by using maple. Okay, so we'll start again, and then we'll define the vectors that we need. So F1 is equal to 2, 4, 5, and R1A is where that force is applied. Then we've got RO, which is just the origin. And what we're going to have is tau naught, torque about the origin, would be equal to R1A minus R naught, and now we're going to need to cross it. And this is the cross product operator in maple. We might need to include linear algebra to make that work. Let's see if it works without it. So that crossed with F1. Yeah, so it doesn't recognize the symbol. This is the error you would get if you didn't actually include that package. We add in the linear algebra package, which is case sensitive, so capital L, capital A, like anything in maple. And now the same command will take the cross product to -6, 4. Looks good. Much faster than writing out this cofactor stuff. So let's think about this. This force is kind of in the positive direction, and so is the moment arm. So the force is probably not going to be that large. How do things work if we take instead, the torque is not going to be that large because they're kind of in the same direction. It's off center a little bit, but not as much as if we were to have a vector that has a larger angle between them. We can find the sine of the angle between them by using the distance thing there, right? So if we take the norm, maybe sine theta, the angle between these vectors that we're crossing must be equal to the magnitude of this tau naught, so that's the norm tau naught 2, divided by the product of norms of those starting vectors. And if we turn that into a floating point, yeah, 0.32. So a lot lower than we would have gotten if the vectors were more perpendicular. Because these vectors are pretty far from perpendicular, we have a lot of reduction just from that angle difference. Okay, so let's compute the next one. We can also figure out the torque that the same force produces about the corner 200. And if you've been just following along at this point, try and stop and work it out. All right, so what we'll do is the same thing we just did, except tau maybe 200 is R1A minus R200. We can define that first. And cross that with F1. Okay, so 244. And we can work out what the angle is between those two. And this one, being at 200, has more of an angle to 45 than the previous one. So we expect to get a larger angle between them than before. Let's check that. So if we take the norm of tau 200 and divide that by the product of those norms, actually here we divided by that one, so we're going to need to use this full vector, the moment arm there. It worked out in the first one because it was a moment arm from 0, so subtracting the R naught didn't really matter. Okay, let's see. So it actually ended up being pretty much the same as before. This means that the angle between these two vectors, like between the force and the original moment arm, R1A, is almost the same as the angle between that and the new moment arm, which is from 200 to R1A. And I drew up a cube here to kind of have a look at this. So here is, let's imagine this back here is the origin on the bottom corner of the cube there, so like that corner. Then this is the x-axis over to the right, and the y-axis would be up, and then the z-axis is kind of out of the page there. And that is how we get a right-handed coordinate system. You need x cross y to give you the z direction. Okay, so this is sort of the direction of the force, right? It's a little bit over in x, 2 to the right, and then it's more in z and in y. That's sort of like a 2, 4, 5 vector there. All right, now if you look at this thing and compare to the vector that's mostly from the bottom corner, it doesn't quite line up, but it's pretty close, then you see that actually the angle between this one and the one from the 200 point, the bottom right corner, is almost the same. Pretty hard to visualize, but this kind of a program makes it a lot easier to see that. So if we want a bigger angle, then we should do something like not 200, but maybe 020. That should give us a better angle from this like top corner, or even better from this corner, which would be 220. So let's check if that works out. If we change it from 200 to 220, then we should get a much better, a much larger sign for this angle between. Let's check. Yeah, so almost twice as good, because now this top right corner here, the vector from this to there, will give us a much closer angle to 90 degrees when we cross that moment arm with this vector. All right, now let's return to point 5 here. I've corrected this from the earlier point in the video. It said accidentally earlier that that the torque produced by this force is the same for all points on the axis containing R naught and parallel to the torque. That's not true, but parallel to the line of action of F, that one is true. Okay, so here's how this works conceptually. If we take F1, which is the thing we're finding the torque about there, and we put it over there, and then maybe we we stretch it, right? So that should be just something parallel to F1. Let's stretch it a fair bit there. Okay, suppose we're going to find the torque not about this point R naught, but about this bottom point here instead. So I think I can maybe create something that does that, like so. This looks good in this dimension. Is it, we're not in the 3D view. Let's see if that looks okay. Oh, that's not very good. Because F1 was not quite in the plane. So we'll have to displace it a bit. Maybe from this direction. We can get it to line up there. Okay, pretty good. All right. So if we are, oh, wait. To displace it, we've got to line up this point. Yeah. Okay. Now we want this R, the new position, to be not that one, but the one that's displaced along the line F naught. Along the line that contains F. Right. So now the new position vector, R naught prime, is down here. Okay. R naught prime. And we'll make this bold. Yeah. So that corresponds to that position vector there. Yeah. Okay. Now this thing, if we were to take the vector that it makes, the displacement from this point to up there, then we would have something that's displaced perfectly in the plane that contains R naught A and the force. So the new R naught A, if we are in the same plane, we'll tell that we're in the same plane because we're perpendicular to the torque there. The new R naught A looks like it'll be something like this. Oh, Let's see. That looks pretty good. I wonder if we're at the right depth. Not quite, eh? Okay, line up like that. Hard to get these fine motions there. Okay, that looks good. All right, so this new displacement one between where we're finding the torque and where the force is applied, F1, this crossed with F1 should give us the exact same torque as we had before. So even though this vector is longer, the amount extra that it's longer has not helped. It's not longer in the way that counts, which is the distance perpendicular from the line of action to this force, right? So this thing here is parallel to this force, meaning that the new extra displacement we've added is just parallel to that force as well. So this force creates the same torque, tau 1, about this point as it does about any point on this line that contains R naught and is parallel to the force direction. We can prove that by taking a cross product. So let's see what that would mean. Maybe we can get everything on the screen at once here. So the cross product, what we're saying is that RA minus R naught crossed with F1, maybe R1A, has to be equal to, since I'm trying to prove this, I won't put the equals there right away, R1A minus this new position, R naught prime, crossed with F1. But R naught prime is on the line of action of the force. The line of action of the force is the line that is parallel to the force. Well, it's not quite on the line of action of the force. It's on a line parallel to the line of action of the force that goes through R naught. So that would be this, where W is some constant. All right, so you can maybe see how this would work out. When you take F1 and cross it with this, we're going to have the same thing as before, but minus this new term, WF. Well, that should be F1, line of action of F1, crossed with F1. But a vector crossed with itself is 0, so we've got that this is just equal to the same torque that we had originally. And you can see that in this picture too. So the extra length of this vector is only extra length in the direction parallel to F1, and that's going to be killed when we take the cross product. What that means is all that mattered about this cross product, all that mattered to figure out the torque, was the part of this that is perpendicular, right? So the distance away perpendicular, meaning that we could kind of imagine extending this and then forming a new vector, which is the smaller one that just shows you the part that's perpendicular to that original F1 vector, and using this to find the torque instead. The advantage is that because these ones are all perpendicular, we don't have to deal with that sign when we're calculating it, and it shows us more directly what the torque is that's created by this vector. Okay, an example. Suppose there's a rectangle that lies in the first quadrant, that is x and y are positive, in the xy plane at z is 0, and it has a length of 5 meters in x and 2 meters in y, and has two forces applied, given by F1 and F2, which are shown here roughly. Find the net force on this rectangle. Then find the net torque on the rectangle about the origin, and find a fast way to visualize the problem and do part B by working with horizontal and vertical components of each force instead of the more manual way. Okay, so net force, we will just add these two together, and that's the net force. So you sum up as vectors the forces applied, and you get the total force. So you can see 2 minus 2 will be 0 in the x, and 3 plus 2 is 5 in y, 0 plus 0 is 0 in z. What about the torque? Torque about the origin, we will need to find the moment arm to each of these locations. Given where they are applied, we've got that F1's moment arm will be this vector. So 0, Ly, 0 crossed with F1, and then F2 will be at Lx, 0, 0 for its moment arm crossed with F2 to get the torque. Okay, so I've worked this out here. We can also double check this with Maple. Control K to put in an execution group. And let's go with R1 is equal to 0, 2, 0, and R2 is equal to 5, 0, 0. Then we'll add in linear algebra. And we will take these cross products. F1 is 2, 3, 0, and F2 is negative 2, 2, 0. Okay, so that means tau 1 about the origin should be equal to R1 cross F1, and tau 2 about the origin will be equal to R2 cross F2. All right, so we got 0, 0, negative 4, and 0, 0, 10. So the net torque will be negative 4 plus 10, 6. Now notice that these forces were entirely in the xy plane, and because the moment arms are also in the xy plane, we're going to be crossing two vectors in the xy plane, so we're guaranteed to get a vector that's in the plus or minus z direction. And that's exactly what happened. We got torques that were negative 4 and plus 10 in z only, and you can use the right-hand rule to check this pretty easily because they're entirely in the xy plane, so it's easier to do that. So we've got this vector crossed F2 will give us a vector out of the page, and that's the plus 10 that we got, whereas this vector cross F1, right-hand rule will tell you that that's into the page, and that's the minus 4 that we got. This hints at an easier way to do these calculations. If you break up F1 and F2 into components, then you can see that really F1's x component was entirely responsible for making this torque because the y component is parallel to the moment arm for F1 when we find the torque about the origin. So that means that to get F1's torque, we can just take this times that length, which is Ly times the x component. So let's see, Ly for that one was 2, right? Times the x component of 2. And we know that that's going to be into the page. So that's where the -4 comes from. And for this one, for F2, we've got our 5 times the y component, which was 2. And that's how you get 10. So this is a much faster way to find out what the torque is in two-dimensional problems like this. So another way to do this that's sometimes convenient is to break up the moment arms into their components perpendicular and parallel to the force vectors and say, you know what, all that matters here is this perpendicular component, like we calculated in that in this 3D example there. All that matters is the perpendicular component to the force. And say, all right, well, we're going to have this times this at a direction which is that cross the force direction out of the page. And this one, we're going to have similarly this cross that into the page. And looking at it this way, it kind of shows you another visual idea, a visual proof of why the torque for F2 would be so much more, even though F1 looks like a bit of a longer vector than F2. It's because this moment arm, the effective moment arm, when you project it onto the perpendicular to F2, is a lot larger for the force, the torque that this produces about the origin than it is for the torque that this produces about the origin. Sometimes you might want to break up both of these into components too. So if you've got an arbitrary application point from of the force, an arbitrary moment arm, I should say, the distance between the vector from where you're finding the torque to where the force is applied, and an arbitrary force. In 2 dimensions, it's pretty convenient rather than taking the full cross product, writing it all out. You know it's going to be in the z direction. So you can just break this into components at the start and say, you know what matters is Rx times Fy out of the page and Ry times Fx into the page. Okay. This idea of the 2D simplifications is going to be a much bigger deal next week when we work with a lot of 2D simplifications. For now, just kind of keep it in mind and hopefully use it to help understand the stuff that we're doing in 3D a little bit better. All right, on to the concept of couples and moments. A couple of forces is a pair of equal and opposite forces applied at different positions to an object. So here we've got F1 and we've got -F1 applied somewhere else. This has the property of creating the same torque about every single point on this object. All right, let's prove this. So if we've got F1, which has these components, then the -F1 has to have these components. Yeah, and let's figure out the torque that this produces about the bottom left, for example. That would be Ly times F1 into the page. And this one, we're going to have an Ly times, I should say Ly times F1x into the page and Ly times F1x out of the page for this, so those cancel. So we end up just with the x component times F1y into the page about this point. What about this point? If we take it about this point instead, then again the x components cancel for the torque, but the y component, now this y component doesn't matter, and we've got this distance times F1y again into the page. So we end up with -Lx F1y regardless of which point you take this about. We can try this out with Maple too. Yeah, so let's start off with, let's just make it from scratch again to kind of lock in the concept of where this goes. So suppose we've got F1, which is equal to 2 and 4. Sure. Now we've also got R1 applied, and let's say that this is at 0 and 2. Sure. Now the other force is going to be -F1, and it's applied at some different spot. So let's say 5, 2. All right. Now what we're going to do is we're going to find the torque, the net torque that these two forces acting together create about a bunch of different points. So let's say R the test point, right? This is where we're going to find the torque. So let's start off with the origin. Add the linear algebra package. And then we'll find the torque. Tau net is equal to R1A minus R test cross F1 plus R2A minus R test, the moment arm from where we're finding the torque to where force 2 is applied, cross F2. Okay, whoops. What did I do incorrectly here? Ah, yes, we've got to make them three-dimensional vectors. So let's just add in an unnecessary third component. This should also work in 3 space too, though. Yeah. So net torque looks like for this setup that it is negative 20. All right, let's change this around. What about the point 200? Negative 20. What about 202? Get some 3-dimension going on in here. Negative 20. So just by the fact that these two forces are equal and opposite, they produce the same torque about every single point on this object. Or indeed, about any point in space, not even a point on the object that we need to be finding the torque about. Yeah, so this kind of non-localized torque is called a moment. If you hear somebody talking about a moment, it means a pure torque that's the same torque about any point on an object or any point in space. It's always created by couples of forces because of this property. So really, moments are applied by couples of forces. You have a force here and a force equal and opposite somewhere else, and this creates a pure twisting tendency on this object. The only component that we really needed was the vertical component, right? The horizontal doesn't matter because that gets canceled out. One way to see this is, since the torque is going to be the same about any point, we can find the torque about any point that's convenient. So let's pick this point. We've got what? This horizontal displacement, the displacement between the points, crossed with that is the same as this component there, right? Crossed with just the y component. So the torque that's created should be the same at any, if you start at any point along the line of action, right? So picking any point along this line of action will make F1, will make negative F1 produce no torque. So we can choose, let's say, this point over here that's convenient, so that the moment arm is perpendicular to F1, and that makes it more clear exactly what the torque is that's produced by a couple, what the moment is that's produced by a couple. It's the size of the force times the separation distance between the force's lines of action. All right, with this concept of couples, we can rewrite the applied forces into the parts that create actually a net force, and then the parts that create a couple. Because a couple creates no net force, right? The force components cancel out. So in this thing, we do have part of that, right? We've got that F1 and F2 had the same x component, but equal and opposite. So that means their x components create a couple. So we could rewrite this as one that doesn't have those canceling x components and just makes it more clear by writing the moment that that couple of forces creates. Okay, so to do this, we're going to break the forces into components. If you draw these same forces in their components, then it looks like this. And now we've got the 2 newtons left for this one and 2 newtons right for that one. The moment is the force magnitude times the line of action separation. This one, because they're just horizontal, you can see the line of action is just this Ly, which was 2 meters. So the moment created by this would be 2 newtons times 2 meters multiplied by the direction. Moment is a vector. So this one would be the r crossed with the force, and you can see that would give you something into the page. Another way to think about it is this force and this force together at the places where they're at will tend to make the object spin around in this clockwise direction. So that's a negative k moment. It ends up being negative 4 Newton meters in the k direction. The way you draw this is with this kind of curly thing like that. In 3D, you could just show it with a regular vector. We could show it with a vector going into the page, but that is a little bit hard to visualize in 2D. So for moments, in a 2D problem like this, you normally will just draw it with this curly arrow thing here and say that it's 4 Newton meters in the clockwise direction. All right, now once we've got that, we can use it to find the net force and net torque about it on the bottom left and top right. So for this system, the net force is going to be just this plus this. It's all in the y direction. It's 5 newtons up, same as we got before. And the net torque about the bottom left, we're only going to need this 2 newtons multiplied by that 5 meters. So that's going to be 10 out, and we've got this 4 in from the moment. So that'll give us a 6 out. Okay. Now what about at the top right? Now we've got 5 times 3 is 15, except this, by the right-hand rule, this vector crossed with that one is going to be into the page. So we've got 15 Newton meters into the page, and then 4 Newton meters more into the page from the moment. The moment just adds the same regardless of what point we're finding the torque about. So we've got 19 Newton meters into the page about the top right, and 6 Newton meters out of the page as the net torque that this setup creates about the bottom left. Now this reproduces the things that we got before for the net torque about the bottom left, and there was an exercise problem up here that had you find it about the top right, and we also reproduced this number in this example as well. The main benefit, though, is not to use it to solve a problem like this slightly more quickly. It's more about the concept of moments. So we're going to need these to understand how supports can maintain static equilibrium, how you could possibly have no net torque about any point on an object by adding something that is going to cause it to cancel appropriately. This idea of this moment that's created by a couple of forces is very important in understanding supports and static equilibrium. Okay, so what is static equilibrium? If an object is fixed in place so it can't move, then it must have no linear or angular acceleration, and therefore, by Newton's second law, must have no net force on it and no net torque on it either, about any point, because otherwise it would be angularly accelerating, right? So this is what it means for the object to be in static equilibrium, not moving and not going to be moving in the future either. So that means that it has no net force or torque on it. So let's suppose that we've got some beam which is fixed into a wall, and the wall is holding it fixed, right? Maybe this is like a flagpole or something that's stuck into a wall over here. And then you put some force on the end of it. The only way that this cannot be moving, and we know it isn't if you've ever tried to push on the end of a flagpole and it holds still, the only way that this can be holding still is if the wall is producing a force that counters the force that you're producing. So the net force on it is 0. Let's imagine it's a light flagpole, so we don't have to worry about gravity or anything. So this force must be canceled with this one, which means the force that the wall applies has to be negative this force. That's what you need for the net force to be 0. But the problem is, unless this force you applied happens to be in a line that cancels, that is collinear with this force, then we're also going to be creating a couple with this, right? Maybe the wall can apply its reaction force down at the bottom or up at the top or something, but for a lot of angles, it's not going to be possible to create no moment with these, which means that the wall also needs to produce a moment in order to hold this thing still. Because if it doesn't produce its own moment to cancel out the moment that's provided by this couple of forces, then we're going to have a net torque on it, and it's going to angularly accelerate, in this case in the clockwise direction. So the wall also needs to produce counterclockwise. Yeah, that's counterclockwise. Yeah. So the wall also needs to produce a moment in the clockwise direction to cancel this. The couple F1 and F wall, which is negative F1, would create a net torque, which is R1A, wherever this force happens to be applied, minus wherever the wall's reaction force ends up being, crossed with F1. And in order to have no net torque on the object, we need the moment that the wall produces to be negative this torque. So that means the wall needs to produce a moment in general, which is negative R1A, where this force is applied, minus where the wall's reaction force happens to be, crossed with the force that we're applying. So now that we're applying this, if you find the net force on this beam, you'll get 0 because this one cancels with that force. And if you find the net torque about any point, you'll get 0 as well, because we've defined this moment so that it perfectly cancels the moment created by the couple of forces. So we can you can check this by finding the torque about this point where the wall is applying its reaction force, and the torque will be the torque from the wall's force, which has no moment arm, crossed with the wall's force, so that's going to give us 0 because there's no moment arm. Then we'll add the applied force torque, the torque that it creates, which is its position, its location, minus the location that we're finding the torque about, which is our WA, the wall's reaction force application point, crossed with this force. And then we're gonna add also the moment that we've applied. And by the definition we had up here, it's actually negative this thing, because that was the moment created by this couple of forces. So they'll cancel, we'll get 0. If we found this about the origin instead, it's the same idea, but instead of subtracting the wall's reaction force to find each of these moment arms, that should be a WA in that one. Whoops, there's an A, yeah. Instead of subtracting WA, we will be subtracting 0 for the two forces. This last one was the moment, and so we don't change what we were doing in there, because this is just added the same no matter where we're finding the torque about the origin or about the application point. So as we confirmed with this check, by adding this moment and this equal and opposite force, the wall is able to set up a situation so that no matter what force we put on this beam, the beam has no net force and no net torque about any point. And that has to be true if the beam is not accelerating, if it's just like stuck in the wall in static equilibrium. So this extends to multiple forces and even moments applied externally to this beam using superposition. You would just say, all right, now the stuff the wall is applying to cancel all of this has to be a net force, which is equal to the sum of the three forces, but then negative. And then the moment would be the sum of the moments we would have had to produce to counteract each of these individual things and to counteract this applied moment, which would be negative that moment. So actually, as we'll see later on in the course, what the wall really does when it needs to respond with some moment, let's suppose this is the moment that the wall is putting on the beam, what it really does is create a distribution of forces, of really stress, like no point force, but like distributed force over the surface here. If it's pulling at the top and pushing at the bottom, that's equivalent to a bunch of couples which have the net effect of creating this moment without creating any net force. If it also is creating a force, it would just shift this around, like have an overall pulling stress or overall pushing stress if it needs to, depending on what it needs to cancel. Another point I mentioned earlier is that we're dealing with right-handed coordinate systems, and these are ones where x cross y is equal to z. So we need this to be the case as long as you want the cross product to work out the way that it's working out. So if 1, 0, 0 crossed 0, 1, 0 is going to be 0, 0, 1, like that's always going to be true by how we've set up cross product, then you need that k hat, the z-axis, points out of the page as long as you want to use the right-hand rule for cross product instead of the left-hand rule. You could have set this up differently, right? You could have said, you know what, let's define it so that we use the left-hand rule for cross product. Then you would have to redefine a bunch of different physics. So if, like, for instance, the force on a moving charged particle by a magnetic field, if this is still going to be QV cross B, then you need to switch which charge is positive and which is negative so that this would work out, or maybe switch what direction of the field is the positive direction of B field, or maybe change it so the magnetic force on a moving particle is negative QV cross B, but you need to switch something if you decide to use a left-handed coordinate system instead. So what I'm trying to say here is double check, don't make Z go into the page if X and Y are like this. It's required to be out of the page by everything that's requiring us to use the right-hand rule. All right, so suppose we have a beam that's fixed into a wall over here, and the wall extends from xy is 0, 0 to 0, 0.1. And the wall is centered on z is 0. And we're going to have moments and forces placed on the beam as shown here at these locations, where F1 is 2, 2 newtons, so 2 in x, 2 in y. F2 is 0, 3, and F3 is 3, negative 3. In addition, we've got a moment, M2 is negative 0.8 Newton meters in the z direction, so it's causing this clockwise rotation because it's in negative k, and it's at the same point as the application point of F2. It's applied by a force distribution there. Right, so find the equivalent net reaction force of the wall and reaction moment that it's applying if the point of application of the reaction force is the midpoint of the wall's contact surface and the origin. So we're going to find out what force and moment the wall needs to apply if it's applying its force here and if it's applying its force there. The force shouldn't depend on what position we apply it at, but if we shift around the force, it could change the amount of the moment that the wall needs to apply. It doesn't change the net force and net torque on this beam. Those should be 0 about every point no matter where we apply this thing. But because we're going to be shifting around this force, let's go back to this simpler picture. If we shift this force down, then it's going to be creating less of a couple with this, so we won't need to apply as strong of a moment from the wall. Okay, really again, it's the superposition of those things that matters, and the wall is producing some stress distribution, which is the same regardless of where we decide we want to put the equivalent point force that is representing what the wall is doing and the equivalent moment that it's creating as a result of where we put that point force. Okay. So the setup of this is going to be that we say that the net force is equal to 0. And the net force is going to be the sum of all these forces, right? So we've got the wall force plus F1 plus F2 plus F3, and therefore the wall force is equal to negative F1 plus F2 plus F3, which in this case is going to be equal to negative, let's just work in 2D here, negative 2, 2 plus 0, 3 and 3, negative 3 newtons, which will give us, let's see, negative 5, and then we've got negative 2 newtons. Okay, so that looks good. That's what the wall has to be applying, regardless of where we end up putting it. Right. Okay, what about the net torque? We're going to say first that the wall has a reaction force at the midpoint of this contact surface, which is at location R W. I think I was calling it RW in this one down here. Oh, maybe not. I didn't give it a name. Okay, let's call it RW, location for the wall's reaction force. So RW is equal to 0 and 0.05 in meters. Then the torque about that point. Wait a minute. So we can find out the torque about any point we like. It's convenient to find it about this point, but it's also convenient to find it about the origin. So let's just find it about the origin. Let's say walls, reaction. So A, suppose the wall's reaction force is at this point, then the net torque about the origin would be the sum of the torques about the origin. Yeah, so this is going to be a vector. And we know that that's going to be, let's put in at the origin is equal to the 0 vector, and this should be the moment applied by the wall plus the RW minus the origin. They're all going to be minus the origin, crossed with FW plus R1 minus the origin, crossed F1. Let's make it a little bit smaller here, plus R2 cross F2 plus R3 cross F3. And then we also have to add this M2. So this lets us figure out what the moment applied by the wall needs to be. Moment applied by the wall must be equal to negative all of this stuff. So negative RW crossed FW, R1 crossed F1, the torque produced by F1 about the origin, torque produced by F2 about the origin, F3 about the origin, and the applied moment M2. The moment that's produced by the wall has to cancel out all of these things. All right, so we can work this out analytically, but it's faster at this point to just jump into Maple and work out all of these cross products without having to calculate them manually. So let's do that. Okay, so we'll take a restart and add in linear algebra because we're going to need some cross products. Now let's add in the forces and where they are located at. So F1 is equal to 2, 2, 0, make them 3 dimensions, and it is located at 0.48, 0.04, and 0. F2 is 0, 3, 0, and is located at 0.3, 0.1, and 0. F3 is 3, negative 3, 0, and is located at R3, which is 0.32, 0, and 0. Let's double check this. F1, 2, 2, 0, 0, 3, 0, 3, negative 3, 0, and the positions 0.48, 0.040 for 1, and then 2 is 0.3.10, 0.3200 for 3. Okay, and now we said the wall force. We calculated this, but let's just find it ourselves. So FW is equal to negative F1 plus F2 plus F3. Negative 5, negative 2, 0. Okay, not surprising. That I mean, that one wasn't too tough, but the moment is a lot more difficult to calculate analytically because of all the cross products we're going to have to take. So Maple really helps out with this one. RW is by definition in this first part 0, 0.05, and 0. So then that means that MW, by the work that we wrote out here, should be negative RW crossed with FW plus R1 crossed with F1 plus R2 crossed with F2 plus R3 crossed with F3 plus M2, which we need to put in. So the applied moment is negative 0.8 in the Z direction. So that'll be 0, 0, negative 0.8. Okay, so let's check. Yeah, so 0, 0, and negative 0.27. We expect something that is entirely in the Z direction because all the forces and moment arms were entirely in the XY plane, and the applied moment was also in the Z direction. So these are just going to create torques in Z, and when you add it to this other torque that's created in Z, we expect that the moment we need to add is also going to be entirely in Z. So yeah, there we go. Now, as a check, we should have gotten the same moment if instead of about the origin, we were finding this about some different point. So let's put in our test is equal to, how about RW for now? And let's modify all of these cross products to be relative to the test position. Okay. So we're going to subtract off the test position for each of these moment arms, rather than subtracting off the origin. And we should get the exact same moment as before. It shouldn't matter where we were saying the net torque is equal to 0 about when we calculate the moment that the wall needs to apply. So yeah, exactly the same. What if we picked a different point? We picked 0, 2, 1. Sure. Any point you like, whether it's on the object or not, will still give you the same reaction moment that the wall needs to apply. Because the whole idea is that the wall is applying this so that there's no net torque about any point. Now what does matter though is where you decide that the wall's reaction force should be. So if instead of 0 and 0.050, we decide that the wall's reaction force is at the origin, which was our part B in this problem, now the moments that we would get, that we would need about any point, rather the moments that the wall would need to apply would be different. So let's check. The net force is mostly over to the right and up a little bit. Right over to the right and up a little bit. And that means that if we were to shift the reaction force down and apply it lower down, we'll probably have less distance for the couple that the reaction force creates with this net applied force. So that means that the wall moment should be lower when we say that the wall's reaction force is lower down on the wall. And let's check. Yeah, so we have less reaction moment there because we reduced the separation distance between the couple created by the wall's reaction force and the net force applied on this object. So quite a large effect of displacing the reaction force vertically a little bit on how much moment the wall needs to apply. That's because the reaction force has a big horizontal component. If we got rid of that horizontal component by instead choosing different values for this, so imagine F2 is now -5. Now we'll have no horizontal component at all, which means that the location that this force is applied on the wall will have no effect on the moment, right? Without a horizontal component, then we're not changing the torque at all by moving this reaction force application up or down. Yeah, so now we have the same result, whether we decide that the reaction force should be at the origin or in the middle. We changed it so that the reaction force is just 0, -2, 0, so it points straight down, and it doesn't matter if you displace that along its line of action. As we learned from before, it creates the same torque about any other point, so that means that it no longer matters where you put the reaction force on the wall. It no longer affects how much the reaction moment needs to be. So in that example, when we had a force that had horizontal components and we displaced it vertically, it affected how much of a moment we needed to add to make an equivalent effect on the object. That is true in general here. So if we take a force, one way to show that this is actually an equivalent effect on the object is to imagine this in stages. So let's suppose you take the same force as this and then you add equal and opposite this on each side in the center. Right. Well, this creates a couple. Yeah. So that shows you that this force is actually totally equivalent in terms of its effect on the object as a displaced force and a couple. So anytime you move the force perpendicular to its line of action, you're creating the same effect on the object as long as you also modify the couple that you're adding to it. Okay, so this setup where we had the beam fixed to the wall and the wall could provide a reaction force and moment, like at whatever level was required to stop it from moving. The wall can totally stop this from moving no matter what other force and torque is placed on this beam. That's called a fixed support. And you could realize this by using a whole bunch of bolts and bolting the beam to the wall, or maybe just gluing it to the wall if you're okay with having a lower maximum strength for this. This is probably not so great for buildings, but it still basically creates a fixed support until it breaks. Even this is going to break eventually. If you put too much force or too much moment, then the idea that the wall can produce enough to stop any motion is going to reach some physical limits. All right, so fixed support is this kind of support to the wall, or really from one object to another, or perhaps from an object to itself. If you imagine splitting the beam, the right side of this has to be in equilibrium too, in static equilibrium. So that means that this interior section must be able to totally stop it from moving, so is also a fixed support, right? The interior of this is just like the fixed connection to the wall and can produce reaction forces and moments. That's going to be a big topic in 2 weeks, where we split up objects into different parts and then learn how to make graphs to describe what's going on internally, which is going to be itself very important for understanding how objects respond to these forces and move in the topic of elasticity, which is a major thing we're going to spend 4 or 5 weeks on. Okay. Now, that's not the only type of support. There's a bunch of other ones that cannot quite produce the same kind of arbitrary forces and moments as the fixed support. Another one is a ball and socket joint. This can produce any force necessary to stop the objects from displacing, but can't resist any rotational motion. They allow all rotational motion, so they will not produce any moment. This is similar to the fixed support, but where it can only produce forces and not moments. That means it won't be able to hold an object still in general by itself, and we'll need some different joint somewhere else to make sure that we're achieving static equilibrium. You have a ball and socket joint in your shoulder and also in your hip. Besides that, there's pin supports. A pin support is like in your knee or elbow. There's not actually a pin there, unless maybe you've had some surgery to add one. It's cartilage, but it acts like a pin. So this is the kind of support like this, where you've got something that allows rotation, but only about one axis. So it doesn't allow any translations, just rotations. You might have it envisioned like this, where you got one solid piece and then another one, and they're frictionless in between them, and there's a frictionless pin that's going through one and into the other one. This allows only rotation and only in one direction, which means that it can apply all 3 force directions and can apply 2 moment directions, 2 perpendicular moment directions, which by superposition could be any moment direction in the combination of those. So like moments in any plane, but it can't resist rotation of this thing, so it can't resist moments that are in the direction of the pin. Now maybe this inspires you into how to make some related joints. This is a slider pin support. So here you have the same idea as the pin one, except that this blue piece has a hole in it, so it can move back and forth like that as well. It can rotate around that point and can move back and forth. So it allows one of the translation directions and one of the rotation directions. It can't resist translations in that direction, and it can't resist rotations about that direction either. So you can see this sort of sliding that way, sliding up, rotating. You could also make a rail joint, which allows only translations but not rotations. So that in that sense, it's kind of like in some ways the opposite of the regular pin joint, right? Which allows one rotation only but nothing else. This allows one translation only but nothing else. Finally, the most freeing joint is the cable connection. So this one allows, it'll allow rotations about any axis. So you could rotate back and around that way, this whole thing like that, and up and down like this one as well. And it also allows translation. So translations like that, or translation like that, but doesn't allow translation only in the direction that would extend the cable. So in other words, it only is able to resist motion by providing a force in exactly one direction, the tension force. we can summarize all of these in a table and talk about the motion that's allowed, the things that it can use to resist relative motion, the motion from one object to the other, and also discuss the idea of degrees of freedom. Degrees of freedom are how many ways this joint allows motion, how many dimensions it allows motion in. So a fixed joint, has no motion allowed between the two objects, no relative motion allowed, meaning it allows 0 degrees of freedom, and it can supply 3 force dimensions and 3 torque dimensions, 3 different moment dimensions to resist relative motion. The ball and socket joint allows rotations only but not translations, so it has 3 rotational degrees of freedom and can supply all 3 force dimensions to resist motion. Pin joint allows only rotations in one axis, one specific one, which has just 1 rotational degree of freedom then. It means it has 1 rotational degree of freedom about the pin axis, and will resist motion with 2 torque dimensions perpendicular to the pin axis, and all 3 force dimensions. Slider pin is similar but with 1 more degree of freedom. It has a rotational and translational degree of freedom. The slider rail, this is another way to show it where we've made the top part extended so it can't rotate anymore, has just the 1 translational degree of freedom, and the cable has kind of 5.5 degrees of freedom, meaning that it allows 3 rotational ones and 2 translational ones, and would allow translation if it was going to be relieving tension in the cable. It only stops translation in the direction that would cause the cable to extend. Okay, let's do a 3D static equilibrium example with some of these special joints. So we've got a cable connection here, and we've got a pin connection from this gray beam BC to this golden beam ABD. Okay, and 2 forces applied. We've got 2 different views, so like an XY plane view and a bit of an isometric view. Let's suppose that point A is fixed to the ground. Point B is a pin joint that is located at these coordinates and allows the gray beam to rotate about it. So it will not be producing a moment that's in the Z direction. It could produce other moments, X and Y moments, and it could produce forces in all 3 directions because it's a pin joint, but no moment about Z. The cable can only produce a tension in the direction along the line from C to D. We've got the coordinates of those points, and we've got the values of the forces and where they are applied. And we're asked to figure out the reaction force and moment provided by the ground at A, and assume that it's applied directly at point A, which is the origin. And we're asked to find the tension in the cable and the reaction force and moment provided to the gray beam by the pin at point B. Then use Newton's third law to check your answers from parts A and part B. What that means is once we found out what these forces are, and we found out what the forces on the gray beam are, this tension and this one, then we will also know all the forces on the golden beam by itself and could use Newton's third law to kind of figure out what these forces are and those forces by using the fact that the force that ABD is applying on BC must be negative the force that BC is applying on ABD. Equal and opposite through that Newton's third law action-reaction pair. Same thing for the tension. The force that this beam is applying here via this cable is equal and opposite to the force that this beam is applying on the golden one via the same cable. So once we've got the things worked out in A and B, we can also use that as a check of the work by figuring out the net force and moment on ABD. All right, let's get going. So first thing, to find out this reaction force and moment, the reaction force and moment at A, we can recognize that the cable and the pin are internal to this system, so we don't really need to worry about that. We'll just view this whole thing as one object and then say that the net force on it from this reaction force plus those 2 forces has to be 0. So for the whole object, we've got that force from A plus F1 plus F2 has to be equal to 0 because that's the net force on the whole thing. So maybe we'll say some of the forces on the whole object is equal to this, and that must be 0. And we also have that the torque about any point on the whole object has to be 0. So some of the torques on the whole object at maybe the origin has to also be equal to 0. And what'll that be? Well, it'll be the RA minus the location of the origin, which is just 0, crossed FA, plus R1. In fact, RA is applied at the origin too, so that's 0 cross FA. R1 cross F1 plus R2 crossed F2. But to make sure that this is 0 for any arbitrary F1 and F2, you can see that this isn't going to cut it. We also are going to need, as usual with a fixed support here, a moment to be applied. Okay, so that tells us what FA has to be and what the moment has to be. All right, let's implement this. Similar setup to last time. Now we've got just 3 dimensions. So F1 is equal to 1, -3, 3 at position R1, 1.3, 0.95, 0.05. F2 is 2, 4, 0. At location R2, 0.5, 1.05, and 0. And then we can figure out what the force at A has to be through FA is equal to negative F1 plus F2, and the moment at A being negative R1 crossed with F1 plus R2 crossed with F2. So let's check. We've got FA is -3, -1, 3. -3, -1, -3, that is. So F1 and F2 together will create 3, 1, and 3. So mostly to the right and in positive Z with a little bit up. And we've got the opposite of that for the force at A. So right and out and a little bit up. And then we've got back and down there. Now it's hard to see on this diagram, considering where they're applied, what kind of moment we would need to cancel that. The out and in, we would need a moment that would tend to make it spin that way about the y-axis. So it tells us that we would need a moment here about the y-axis, which would make it spin in the other way. So that means that you expect a positive moment about the y-axis. All right, good. And we've got a positive one about Z too. What is that? Does that make sense? What would make a Z moment? That would be if the X force, so X force here is positive and it's mostly displaced up, and the X force here is negative, which means that it would be spinning about the Z-axis in this direction, unless we apply a positive Z moment to cancel it, and that's what we found as well. Okay, so bit of a check. Seems like it's working out so far. Okay, now let's talk about what's going on the gray beam. So in the gray beam, we've got a force from the cable, and the force of the cable on the gray beam we can call maybe CD, force from C to D, and we don't know how strong this is. The cable could have any amount of tension in it. Let's call it actually tension, and what we do know is the direction of it. So we know that this is going to be in the direction of the unit vector pointing from C to D. I mean, it's also in the direction from C to D, but then we would not have exactly the tension as the scaling factor. So by making this a unit vector, we end up with just the tension as the scaling factor, and tension has some meaning, so that's kind of nice. So we'll say that this is equal to the tension times the vector from C to D. And the vector from C to D would be R final minus R initial. So RD minus RC, like usual. Let's call this, well, I mean, that's RCD, so that's fine. Over the magnitude of itself. That's how you make a unit vector. Okay, so that's what we know about the force. The reason you want to do this is because this points out that it's not just an arbitrary, totally unknown thing. We actually know it down to only one scalar unknown, right? There's only one parameter that we don't know about this tension, which is, well, the tension. The force provided by this cable is known in direction, just not in magnitude. Okay, what about the reaction force from pin B? We've got that could be any force. right? FB is equal to 3D, FBX, FBY, and FBZ. And it also can produce a moment. Moment applied by B. These are the forces that the golden beam applies to the gray beam. The moment, what do we know about that? It also is an arbitrary moment in X and Y, but we know that there's no moment about Z because the pin is in that direction. So this can't be providing a moment about Z. It can't be resisting rotations about Z. All right, now we're in a position to again use Newton's second law. On B, we'll have that F1, or actually, well, let's just start off with the sum of the forces is equal to 0 is equal to F1 plus F2. Those are both acting on the gray beam. Oh, I said on B. I meant on the gray beam. On the gray beam, sure, title case, why not? F1 plus F2 plus the force from B. This is the force of ABD on the gray beam. And the torque about, I mean, again, we could find the torque about the origin just to make it a little bit more, a little bit easier to solve by eliminating some forces. Maybe it's better to find the torque about pin B. So sum of the torque at B on this beam has to also be equal to 0, and that will be, let's see. So the moment that we're applying, that the pin is applying on this gray beam at B, which again has no Z component, plus the moment arm to force 1's application point, which will be R1 minus RB cross F1, plus the moment arm to force 2's application point, R2 minus RB cross F2. And then the same thing for the cable, plus RC minus RB crossed with the cable force. Okay, so this is also equal to 0, and this gives us an equation we can use to solve for the moment. Oh, wait a minute, I forgot the cable force in this first one. Right, so we've also got the cable force acting on the beam. Right, now this one has 3 equations, so it's like X, Y, and Z components of this, but 4 unknowns because we've got 3 unknowns for the force on B and 1 unknown for the cable force. So we won't be able to solve this one first. We'll have to solve this one first, which has 2 unknowns for moment and 1 unknown for the tension in the cable. Or we could take all 6 of them and solve them at once. Yeah, let's do this one thing at a time first. Let's first try and solve this moment one and then the force one. So we can put in RC, which is 1.5, 1.050. And RD, which is 0.0520. And I guess we'll also need RB, which is 0.110. Okay, so then the next part is we can specify the what FCD is, which is going to be the tension times RD minus RC over the norm of RD minus RC. So this should give us a vector that points in the direction of CD. So C and D have the same Z component, which means we don't expect any Z part of that, and it should point back and up. It looks like it points in negative X fairly strongly, and in positive Y not as strongly. Right, okay, that looks good. Next, we can use this net torque equation about point B that we found. So net torque about point B is going to be MB, this thing we worked out down here, the moment that pin B applies, plus R1 minus RB crossed with F1, plus R2 minus RB crossed with F2, plus RC minus RB crossed with FCD. So that'll be the torque equation. What did we do wrong here? Invalid, oh, and X, yeah, and X. That's the cross product one. Okay, so we don't know what MB is. We didn't put that in yet, but we can first put it in as a variable, right? MB is equal to MBX, MBY, and 0. Specify that and that additional information. Now we can kind of combine them and get these three different equations. So if this is supposed to be the 0 vector, you can see from these different parts what MBX, MBY, and the tension have to be. So let's kind of solve that. Well, first let's go through. How can we separate this out? We'll use the sequence function. Sequence is a useful thing. You can say n equals 1 to 3, something like that. And that'll just do whatever thing you put here, in this case n, for each value of n you specified in a comma separated list. So that's pretty useful for this, because now we can pull out the three different equations from the torque equation. So we'll say sequence tau equation n equals 1 to 3. And this is going to use the subscripting thing to get the components from this vector out as a list of comma separated terms, which we can then put into the solve function. Whoops. Where did I mess up? Oh yeah, we have to now put that into a square bracket to make it the first argument that we're giving the solve function, the set of equations. Okay, so this is the net torque, which is supposed to be 0. We've passed this, this, and this as the equations to solve. And when you tell solve something that's just one side of an equation, it assumes you mean equals 0. So now it's gone through and solved for those three parameters. All right, we can assign that. And then use the force equation to find out what FB has to be. And then we'll have FB as well. So we got it all. So let's see here. The force that we're applying from B is left and down and back in Z. The tension ended up being positive. That's good, because otherwise it would mean that this doesn't hold. It's kind of flipping up like that, and we can't stop that with what with the cable. So we've got a positive tension. We only needed a moment about the y-axis. MBY is positive. That means we needed to stop this beam from pivoting out this way from F1's Z component. That would have caused that to happen. So we are canceling that with a Z component of our own in the opposite direction, but those two together would create a couple, causing this to twist. So we cancel that with a positive Y moment on this beam applied by B. Yeah. Okay, now it's actually easier to write the equations if you don't have to subtract off this RB position. You find this torque about the origin. But the problem is then you would have had to deal with the fact that FB would no longer be eliminated, right? So we would have had RB crossed FB plus MB, and then this is just R1 cross F1, R2 cross F2, and RC cross FCD. And this extra set of the three unknowns here is worse, because then you can't solve it in stages, right? We can't do what we just did, where we said, hey, we've only got three unknowns in this equation, solve for those. And then after that, we've got only three unknowns in this equation, so solve for those. But with Maple, it's not really that big of a deal, right? We could go back to this same setup here. and modify the torque equation to now be this new one, RB cross FB plus MB, and then just make this R1, R2, RC. And now we simultaneously will need to solve the torque equation and the force equation. So we can set up the force one similar to what we did here with unknowns. And then say that the force equation, instead of this, is the sum of all the forces on this gray beam. Then what we're solving is the terms in the torque equation and the terms in the force equation. I think, yeah, let's just put two different sequences. No need to be too fancy here. So sequence F equation as well. Maybe let's just put this on its own line to see what we're getting there. Okay. So we've got all the different force equations and what should have been the torque equation, but it looks like we messed up. So we've got FC, and it's not sure what that is. I might have erased the wrong part in here. Okay, let's see. Oh, FCD is what this was supposed to be. All right. So all the different force equations and torque equations, then simultaneously solving all 6 of them, and we get the same things as we were getting for those values earlier. The final part is a check, which is now that we've figured out the force that ABD is putting on the gray beam and through both this pin and the cable, and we found out the reaction force that has to be at A, we can also check that there's no net force or torque on ABD. So for that, we'll say the net force on ABD, well, let's make it a vector actually, force on ABD would be equal to the force from A. So if FB was the force that ABD is putting on BC, then we're going to be subtracting FB, because negative FB would be the force that this gray beam is putting on ABD. And we're also going to be subtracting FCD, because similarly that's the opposite of the cable force that is being put by ABD on BC. And this is supposed to be 0. And we'll also check the net torque on ABD about any point, let's say the origin. And that'll be, well, there's no torque from FA because that's at 0. Just say 0 cross FA plus the moment at A, and then all the reactions from this. So that'll be plus RB crossed with negative FB, RD crossed with negative FCD, because this is applied at that point D. Now FCD is along this line of action, so it actually should give us the same torque as if we were to cross not RD, but RC with that, because that's displaced along the line of action of the force. And then we've also got the moment. So if MB was the moment that ABD is putting on BC, then negative MB will be the moment that BC is putting on ABD. Okay, so we can check this and see if we actually get no net torque and no force on ABD using the values we calculated earlier. Okay, so now that we've got this solved and assigned, doesn't matter whether we use the one where we did it all in one solve or in stages. Let's check what this net force is. FA, let's call this ABD, Fnet ABD, yeah. And this is going to be FA minus FB minus FCD. And we're also going to check tau net ABD, which will be MA plus RB crossed with negative FB plus RD crossed with negative FCD minus MB. Let's check. Moment of truth. Okay, zeros. So 10 to the negative 9 and 10 to the negative 15, 10 to the negative 8, 0 within the precision that we're working with. So that's great. That means that using Newton's third law, we were able to confirm that the forces that ABD is putting on BC, when we take the Newton's third law action-reaction pairs for those and find the forces that BC is putting on ABD, and add that to the reaction force we found on A at the beginning, we do indeed get no net force and no net moment on ABD. Other part, it shouldn't matter whether we really used RC for this or RD. Yeah, because the line of action of the force should make no difference between that. So if we use RC, we still get 0. If we use RD, 0 as well. Similarly, up here, when we were finding the torque on BC, we could have used RD because it's along the line of action with that force. And yeah, we found the same torque that way as we found earlier. So a couple of concluding notes here. You probably noticed that it didn't matter whether we took the torque about the origin or about point B, we were still able to solve it. The equations are maybe a little bit nicer one way than the other, but you can still solve it. So that means the new torque equation doesn't give conflicting information with the original torque equation. It does give different information than that torque equation, but it still creates linearly dependent equations on the whole set of the original torque and force equations. So the most straightforward way to do this is to use the force equations and then the torque about any point that you like to get the torque equations. But sometimes it's convenient to get targeted equations, get the equations that you're looking for directly by using more than one torque equation instead of one or all of the force equations. So you can try this out. Torque about B and the torque about 0 together don't quite allow you to solve for everything. So there's not, these are not totally a linearly independent set when you combine them all together, because we've got one thing that hasn't been solved for. There's at least one equation in this set which is linearly dependent on one of the equations in this set. You can see this by eliminating one of the equations and showing that we get exactly the same things solved for. We still don't have FBY. We're still kind of out one thing that's unknown there. And if we add in either the X or Y force equation, it turns out to fix it, but the Z force equation doesn't add enough. And you can even fix it by adding in a special torque equation, like the torque about this extra point E defined here. Now this does give enough information to let you use just torque equations to solve for all of the things that we're looking for. One thing to definitely keep in mind with this, though, is that if you have redundant equations, then even though they're supposed to add no new information, with round-off error, Maple can get tricked and think that two equations which are really close together, let's imagine you have, I'll exaggerate the round-off error. Let's imagine you were saying x plus y is equal to 3, right? And then you're also saying like x minus y is equal to 3. Well, you probably can see the solution to this right away. So y equals 0, x equals 3. Fine. Fair enough. But let's suppose that you add in another equation which is redundant. 2x plus 2.00001y is equal to 6. Right. Well, the problem with this, actually, I guess this one's still true. Let's do it like this, because y was 0. Yeah. Problem with this is really this is from a round-off error in the coefficients. But if you combine these together, it will give you a different answer technically than the original ones were giving you. So you didn't mean this. This is just a round. You can tell by looking at it that this is just a round-off error compared to the other equations. But Maple doesn't really have a way of knowing that. So if you give it redundant equations, if you know that you should only have 6 linearly independent ones, but you're not sure where to take the torque, and you just put in 4 sets of torque equations, so 12 different equations, then likely you're going to end up with a different solution, or maybe even no solution, if it chooses to solve some of them first compared to what you would have solved due to these round-off error things. So with round-off error in the mix, things that are really dependent on each other can appear like independent equations and end up giving you no solution, or at least a different solution if you don't have the full set of them than you're supposed to get. In this example, I mean, we solved we solved problems earlier where we had a fixed support and we were able to totally find out what was going on at the reaction with the support reaction, given arbitrary forces and moments on it. And then in this example, we had a pin support and a cable, and we're able to solve for it. Notice that we had 6 equations and we had exactly 6 unknowns set up in the right way to let us solve for it. This system is externally statically determinate because of that setup there. So if you were to get rid of the cable, now what happens is this beam would not hold up, right? This would fall down. We would have still 6 equations, but only 5 unknowns to use, and that means that there might not be any solution, right? We don't have enough kind of unknowns to solve for to let us find a solution that holds this thing up. From the physics perspective, there's no cable there, so there's directly no way to cancel the torque that these forces would be producing about this point, because the pin can't produce a counteracting moment, so this is going to fall down. Alternatively, if we had a fixed support here, now it's not going to fall, so we have a different problem. This one where we can't solve for it is called statically underdeterminate. That's a big problem because the structure is not going to be really in static equilibrium. This one is a problem for now. So this is over-constrained from the structural sense. We've got too many supports, over-supported. But that means that the equations that we set up, we have an extra unknown, right? We still have 6 equations, but now we're going to have 7 unknowns. The 3 forces and 3 moments for this fixed support, plus the tension in the cable. So we can no longer solve for it unless you get extra information. One extra information is to ask the kind of question like, find the reaction at the fixed support B if the tension in the cable is 0. So you basically imagine you're asking the question, what if the tension is not there? Or what would this have to be so that there actually isn't any tension in the cable? Or what's the tension in the cable if support B has no force in the Z direction? So you can ask all kinds of, now this one I think doesn't work because the cable is directly in the Z direction. So not all of these questions that eliminate the variable eliminated in the right way to get the problem to a position where it's solvable. Still, by eliminating a variable or asking some extra information about the variable, you can now solve this sort of a system. This setup, where you can't solve for it unless you get extra information, but it is going to be in static equilibrium, even though you can't solve for what the values of the forces and moments are, is called external static indeterminacy. So it's indeterminate what the forces and moments are going to be, but you know that it's going to hold still. We will be able to solve for that in a few weeks after we learn about elasticity and figure out how the beam is going to deform and respond in response, well, how it's going to deform in response to the forces and moments that are on it. The internal forces and moments leading to stresses will cause it to bend elastically, and that will give us some extra information about how it will respond in light of any supporting that we're giving it and resolve this indeterminacy that we're dealing with for now. So today we looked at how to find the torque about a point, including the idea of position vectors. We looked at how equal and opposite forces create a force couple that produces a moment, which is something that's like a torque, but it's the same torque about every point on the object. Then we looked at the idea of static equilibrium and how wall reactions can stop externally applied forces on this by applying their own externally applied force to this object, but that also requires an externally applied moment. We looked at how these are really produced with distributions of forces in the connection and looked at different joints. And besides the fixed support here, we looked at how these different joints are able to resist motion and have various degrees of freedom that still allow some motion in directions that they can't resist. The directions that they can resist allows you to set up problems and solve for unknown forces and moments in the joints, as long as the system that you've got is externally statically determinate. If there's not enough supports, then you can end up with a statically underdeterminate system, which is not in static equilibrium. If you have too many supports, then you can have a system that is statically indeterminate, which means it will still hold still, but you won't be able to solve for the joint reaction forces and moments unless you're given other information, at least for now. Thanks for watching. I'll see you next time.